Okay, let me share my screen. Jaren, are you able to see my screen?
Yes, ma'am.
Okay, okay. I welcome you for the week 8 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Okay, this session, it's going to be an interactive session. Okay, and I'm just switching off my video for the internet issue. I think due to rains, I'm having some internet issue. I'm just switching off my video so that we are connected. Okay, there is no lag in the connection. Uh, okay, this is going to be an interactive session. So feel free to answer. Okay, there is nothing right and wrong. Okay, it's going to be a learning process. Okay, hello,
Okay,
Jaren.
ma'am.
Yeah. Okay, so let's get on to the session. Uh, so we'll begin with a brief recap of lectures of week 8. Okay, so lectures of week 8 were on we had about 9 lectures, correct?
Yes, ma'am.
Yeah, were you able to go through the lectures?
I haven't got the time for that, ma'am. I'll
Okay,
be doing it in the last few weeks, ma'am.
okay. Not an issue. One second, I'll just check if my recording is, sorry, if my recording is happening. Okay, you're able to hear me, right?
Yes, ma'am.
Okay. Okay, let's get on to the session. So before we get on to the actual practice assignments, we'll have a brief recap of lectures of week 8. So lectures of week 8, it covered two different topics. One was on continuation of viscoelasticity in polymers. The second was on interaction of polymers with other materials. So on viscoelasticity of polymers, we had few lectures, and then the remaining lectures of the week 8 were on interaction of polymers with other materials. So in viscoelasticity in polymers, the first lecture, lecture 53, was on testing for applications. So it was on uses. Okay. Here, different trade tests were discussed for measurement of different properties. That is, for example, you will, identify modulus, tensile strength, all these, the material property and all you will be determining it, right? Whereas for the trade or commercial purposes, there are certain tests that are done, okay, for different applications. So these tests were, explained in the uh, lecture 53. Okay, so what are the, different types of trade test, for what are the, what are the material, properties you could, estimate using trade test was discussed. Okay, some of, for example, so certain trade tests can be on measurement of hardness and scratch resistance, puncture resistance, tear strength. So these are, some of the parameters for which trade tests are available. Okay, and one more thing is that these trade tests, the parameter, the property what you get from the trade test are not material property. Material property in the sense, it is not, the property of that of the material, unanimously, or as a common this one. It is for that particular test, for that particular specimen, that the trade test value is applicable. Okay. uh, and there may be, different measures for different applications also. The trade test may vary also depending on the application. So for one, you may need to measure at hardness. For one, you may need to measure, scratch resistance. So depending on those, the trade test may vary from application to application. And also, the value obtained in one test may not be, a suitable value for another application also. So this is also, explained in the lecture. Okay, and then one of the parameters, this hardness, it can be tested using different trade tests for different class of polymers. So there are tests called Story hardness tester, Shorty hardness tester, Rockwell tester. So these were all discussed, and it all these trade tests, it gives a number, like for example numbers hardness in the range of 1 to 100. Okay, or some other parameter, maybe absorption coefficient in certain numbers. Okay, or abrasion and wear in certain numbers, like 1 to 100. If the abrasion number is 1, there is, it means this is the behavior. If the abrasion number is 100, it is, this is the behavior. So these also varies. Okay, uh, these also varies. And the next concept that was discussed was volume and surface resistivity. While volume resistivity, it is a material property, whereas surface resistivity, it may vary from surface to surface to what the polymer is actually exposed to. In some case, the polymer may be exposed to water or some polar solvents. So that time, that surface will be interacting with the polar solvent, so the conductivity will be different from when it is exposed to air or some dust. Okay, so based on this, the surface resistivity will vary, whereas the volume resistivity is uniform. Okay, so resistivity is a property of the material. So this concept was also discussed in the uh, testing for application, where trade test was majorly discussed. Okay, you're able to follow.
Yes, ma'am.
Okay, yeah. So this actually, majorly trade tests were all discussed in the lecture 53. And then the lecture 54, the properties of blends was discussed. Okay, now how the glass transition may vary with for blends, and how does it differ with the miscibility of the blend. For example, a pure polymer may have a different glass transition temperature, whereas a miscible blend of two different polymers, it will have a different glass transition temperature. Okay, where the segmental mobility will be possible, that temperature will be the demarcating temperature will be different. And this also, it depends on the miscibility of the polymer also. For example, two polymers, if they are completely miscible, they will have a single glass transition somewhere in between, the individual polymer glass transition temperature. Whereas an immiscible, blend of two polymers, it might have two glass transition temperature. One corresponding to the, closer to the temperature of the polymer, having a particular temperature, individual polymer having temperature, and there can be another step in the another glass transition temperature, which is closer to the second polymer. So it will be having two glass transition temperature. From the glass transition temperature also, you can identify whether the polymer is miscible or immiscible. For example, if it is going to have two glass transition temperature, a polymer blend, you know that this is a polymer blend, and determine the glass transition temperature. And if you find two glass transition step change in, for example, in a DST testing, okay, then you will see that you can identify that it is an immiscible blend of these two polymers. Okay, and also, the polymer properties also, they may have, when they are as blends or when they are copolymers, the property, for example conductivity. Okay, if there is a blend of two polymers, or if there is a copolymer, it can be either additive. Additive means, like polymer 1 has a conductivity of 10, okay, and polymer 2 has a conductivity of 100. Okay, uh, Siemens per centimeter. Okay, so the blend may have 100 plus 10, 110. That is nothing but just an additive effect. Whereas there can be cases where there can be, it need not be 110, but it may result in conductivity of 200. Okay, or modulus of 200, unlike an addition, which an additive effect which gives 110. Okay, or it can be negative synergistic effect also. Okay, where when you have the blend or a copolymer of two polymers, it can have a negative effect of synergism also, where the overall combination will have a lower, very low modulus compared to the individual polymers. That can also be, the synergism can be a positive also, can be negative also. So that was discussed, and in fact an example was discussed in terms of your impact strength of a copolymer and a blend of polyethylene and polypropylene was discussed, where the blend of polyethylene and polypropylene, it gives an additive effect in terms of impact strength, whereas when it is a copolymer, it gives a synergistic effect. In fact, there will be a point, if you observe the curve, given in the lecture, you could observe the curve, you could find that there is no fracture in the copolymer system. So that is how the synergistic effect has happened for the polypropylene and polyethylene copolymer, okay, system. Okay, and the next aspect that was discussed was on toughening in polymers, where an example of epoxy with rubber particles was discussed, where a table was given mentioning different properties of a pure epoxy and a epoxy modified with rubber particles, and it was observed that the values of fracture energy and the isotope impact strength increases significantly when there are rubber particles. So it has toughened the material. Okay, it has given better impact behavior for the material. Okay, and then blends, there was also an example of blends of conducting polymer. So here the example discussed was on the polyaniline. It is a conducting polymer, right? Hello.
Yes, ma'am.
Yeah, it is a conducting polymer, right? So
Yes, ma'am.
it has conjugations, and it has a conductivity, right? Intrinsically conducting polymer because of the conjugation or delocalization of electron in its structure. But the problem with this polyaniline is that it can the film formed out of polyaniline are very brittle. Okay, so for the purpose of increasing the processability and film forming capability, they blend it with different polymers like PVA. Okay, so when you blend this pani with PVA, so there will be some composition of this PVA and pani, right? That is polyaniline and PVA. So it was observed that when you have a pure PVA, and when you add nearly 30% of polyaniline to that, the conductivity increases several folds. There's multiple orders of magnitude increase in the conductivity. Okay, so this was also discussed in blends of conducting polymers, where while discussion on properties of blends. So these were all main contents discussed in the properties of blends. The next lecture, it was on biomimetic polymers. So have you heard of this term biomimicking?
Yes, ma'am.
You have heard of this term biomimicking. Where have you heard of this term, and do you have any idea or example on this biomimicking where it is being done?
No, ma'am.
Okay, so the concepts of biomimetic devices were discussed. So biomimicking can be, for example, based on a member, like a soft robo. It is a biomimic of some natural uh, material, or a natural, for example, biomimicking, inchworm, it moves like, it will move in an inch and then it will flatten out. You would have seen some worms moving like, they take a curve and then they flatten out and then move. That is how their movement will be, correct? Have you seen that?
Yes, ma'am.
Yeah, so that kind of locomotion can be biomimicked. Okay, or there can be a biomimetic device, right? Like artificial skin, artificial nose. Okay, or there can be a biomimicking of feature also, like for example, lotus leaf. You would have seen the latex in lotus leaf, right? And there'll be some surface patterns in lotus leaf, that it the water does not wet the lotus leaf, but it will form kind of a droplet and fall off, correct? So that kind of a pattern can also be biomimicked. Okay, so it can, so different aspects of biomimicking can be done. So a question comes here, where can we use polymers which mimic the natural biological organisms. And two concepts of biomimetic polymers were discussed in this aspect. Okay, one was on synovial fluid. So this synovial fluid, for example, it is actually present in all joints in our body. Okay, and the role of this synovial fluid is, you know lubrication. Okay, and the friction coefficient of this synovial fluid is very very low. Okay, it is having a very good lubricating effect, and has a friction coefficient. It is a measure of the lubrication. Okay, so the friction coefficient, for example, for a synovial fluid is 0.002 to 0.003. Okay, so whereas, it is even less than the coefficient of friction coefficient of ice. We know that, in ice, if there is a surface of ice, people tend to slip, right? You would have also seen this ice skating and all, right? People used to slip and all, right?
Yes, ma'am.
Yeah. So the friction coefficient of ice is, 0.02 to 0.05, whereas friction coefficient of synovial fluid is much much lower than that. I told that, no, it is 0.002 to 0.03. So can we biomimic that kind of a behavior in polymers? So for example, the structural, properties, or structural, how it is, structural arrangement of synovial fluid is made up of, was discussed. Like it has multiple layers, like base layer, anchor layer, hydrated layer was discussed. And one of the major component, which plays a lubricating effect in synovial fluid is mucin. So mucin has some branched architecture and some functional groups and all. Okay, so can we biomimic, with other polymers, these features? Was discussed. And next is, uh, you know, uh, the next discussion was on, can we biomimic collagen? If you look into the structure of collagen, they have beautiful hierarchical arrangement. Okay, if you go through the lecture, you will see the figure how it is like hierarchically aligned. They form, helical structure, and then they, two polymer chains, they then interact, and then they form double helix, and then they have some, kind of a fibrillar arrangement, and this fibrils, they form bundles. So can we biomimic this kind of an arrangement of collagen in other polymers, for to get certain properties, like for to have some certain, stimulus response, or some electroactive polymer response, or some dielectric response, or something. Can we develop biomimetic polymers? So whole lecture was on, can we develop some biomimetic polymers which mimic the natural materials or biological organism was. So through citation of different examples, this, thought process was, brought in. Okay, so this was all about the lecture 55, which was on biomimetic polymers. The next lecture was on advanced mechanics. Okay, so in advanced mechanics, the phenomenological description of mechanical response, where, the mechanical analogs were discussed. Do you remember what is a mechanical analog for elastic response or elastic behavior? This was even discussed in week 7 lectures. Any memory?
No, ma'am.
Okay, so, response can be, the mechanical analog for elastic is a spring element. Okay, whereas for a viscous response, it is a dashpot, and for a, plastic response, it is a sliding element. Okay, and the overall material response can be a combination of these springs, dashpot, and uh, sliding element in parallel and series combination, in order to develop the overall, how the, to develop a overall model for a particular material, polymer material behavior. Okay, so you can have, one spring and one dashpot in series. Okay, which is a Maxwell model actually, or spring and dashpot in parallel, which is a Voigt model. Okay, so or you can have a spring and two dashboards. So these kind of, to in order to develop, or in order to understand the overall polymeric macromolecular behavior, these combination of these mechanical analogs can be used. Okay, and the spring can be also a linear spring or a non-linear spring also. Okay, the next concept that was discussed was on failure. Okay, and the crack growth mechanism, the Griffith's hypothesis was discussed, and how, what are the different crack growth mechanisms for different kinds of polymers. For example, for a glassy thermoplastic polymer, it may be, entanglements, orientation, and crazing. These phenomenon may lead to some crack growth mechanism. Okay, whereas in case of thermosets are nothing but they are cross-linked network. Correct, thermosets are
Yes,
cross.
ma'am.
Yes. Okay, so these cross-linked networks, then the crack growth, maybe due to some chain stretching or crazing. Okay, between the crosslinks. Okay, and then there was a discussion on rubber. In case of rubber, what happens is that the segmental flexibility, due to its segmental flexibility, the dissipation of energy is more compared to the actual fracture process. Okay, and how, the fillers present, in polymer composites, they have an impact. So these were all discussed in the crack growth mechanism. The next concept was on fatigue mechanism. Okay, where in fatigue, actually your load is actually lower than the actual strength of the material, but it is a prolonged load and a cyclic loading. Okay, you load and unload, you load and unload, this kind of a cycle. So the material fails because of fatigue. Okay, and then a summary of the mechanical response on the polymer structure was discussed, where, what are the responses when, where there is no damage in the material. So there can be an elastic response, and this elastic response can be a linear elastic response or a non-linear elastic response. There can be a viscoelastic response, or there can be a plastic response. So these are the mechanical responses where there are no damage to the material happening, but there will be a changes in the microstructure of the material. But there are, you know uh, mechanical responses, or situations where there is a structural change. In addition to that, there is a damage also happening. For example, in case of impact, in case of failure and fracture and fatigue. So these cases, damage also occurs in addition to the structural changes that is happening. Okay, so these were all discussed in the advanced mechanics lecture. The next lecture was on viscoelastic response. Here, there was a description on the master curves. For the master curve description, the creep compliance of polystyrene was discussed at different temperature, and how, you develop a master curve based on the experimental measurement was discussed. And then dielectric response of polyvinyl alcohol was discussed. Okay, and one more concept that was discussed is that, for example, creep response, the relaxation times may be different for a mechanical response. For a dielectric response, the relaxation times may be different, right? And for different, as a macromolecular nature itself, for each of these responses, there will be, different relaxation times involved, correct, to have these responses. But, you know and the different techniques, it measures, different, relaxation times, or right. But the overall, nature of response, it does not change. Okay, so you can have master curves of a dielectric response, and it will again show your glassy behavior, and then it will show your rubbery behavior also. Similarly, in creep compliance also, it will show how the behavior will be in glassy nature, and how the behavior will be in a rubbery nature. Though the time scales for each of these responses are different, but the overall nature of the response will be similar. Okay. For example, in rubbery behavior, you can, from the nature of response itself, you will find that this is a rubbery behavior, and you could identify there will be a segmental mobility in that particular behavior. Okay. So this was also brought in. Okay. Are you able to follow?
Yes, ma'am.
Okay. Okay. If you are not able to follow, you can just you can just you have some question. You have raised your hand.
No, ma'am. That's the accident.
Okay, accidentally it happened. No issues. Now let's proceed with the next. So the next set of lectures they're basically on interaction of polymers with other materials. Okay, and so the main the next the lecture 58 was on polymer packaging. You know that polymers are used for packaging, right?
Yes, ma'am.
Yes, right from your milk packet you get it's polymer, correct? Or your Lay's chips packet, again it's a polymer, right? And in fact it will have multiple layers also, it's not a single layer. Okay, and the role of polymer will also be different. They can be a barrier films. For example, in Lay's chips packet, in the packaging should be such that it should not allow penetration of moisture or penetration of oxygen, correct? Because the material inside, the food inside, the chips inside, if your moisture is going to get inside the packaging, then your chips will become soggy, correct? You will not buy the chips, correct? So it should have that barrier property against moisture, correct?
Yes, ma'am.
Yeah. And then there are certain instances where your impact resistance, especially when you're transporting material through long distances, so the polymeric packaging should bear that impact, right? Because it may be you may transport it through flight, you may transport it through a car or a bus or a truck. So in these cases, your impact resistance of the packaging becomes important. And there can also be packaging, kind of secondary packaging. This actually does not play a role in like barrier properties or impact properties, but they can be kind of aesthetically important, to give kind of a good appearance. You will have some polymer coating, or polymeric packaging, secondary packaging. Or for example, you can uh, you can just imagine your Lace packet itself. You have something printed, you have this potato chips images and all in your Lace packet, right? Correct.
Yes, ma'am.
Yeah. And there is also some writing and all. For example, the name of the product, the brand name, the company the manufacturers. So for printing all these, every polymer will not give this printability, or every material will not give this printability effect. So in order to have some kind of these printability effect, there are some secondary packagings that are required to have that better printing, so that you are able to see that pack, all the things printed, beautifully. Okay. And then packaging is also used in electronic components, correct? For example, your laptop also, right? It is also made up of some polymer, correct? Your external surface of your laptop is made up of some polymer. And it demarcates different components, right? Your semiconductors, it will demarcate, and some other connections it will separate out, right? So that there is no shorting and all, correct? So that was also discussed. And then what about renewability of packaging? And then one more important thing that was discussed is that, so polymers are used for packaging, that is known. But what is the percentage of polymers used in packaging sector? Any idea? Nearly 40% of the packaging materials are made of polymers. And of these, 95% uses either polyethylene, polypropylene, polyethylene terephthalate, or polystyrene. So that means a lot of percentage of polymers which are used in packaging are non-renewable, are derived from non-renewable sources, correct? Right? Polyethylene, for example, it is from a non-renewable source, right?
Yes, ma'am.
Yeah. Whichever polyethylene is manufactured is from non-renewable source. So why can't we think of the renewable packaging material? And also recycling of packaging material. For example, renewable packaging material means, why can't we mix cellulose with the polyethylene? Or you can just use cellulose as a packaging material, or starch as a packaging material, or some proteins like casein as a packaging material, right? So these aspects were all discussed. Okay. So, and then the next concept discussed was on barrier films. What are the important phenomena associated with barrier films? So obviously barrier films means it should create a barrier, or it should inhibit certain movement, correct? It should inhibit, for example, oxygen to travel through, right? So when there's a movement of small molecules, or when you want to inhibit small molecules movement, then what are the properties that you have to think about? You have to think on diffusion. How is the diffusivity, or how much it is going to absorb some materials from the external environment, or what is the absorption, or what is leaching out of, sometimes materials should also not leach out of the packaging, right? It should not reach out, leach out to, for example, say for example, the packaging, for example, the printing ink should not leach out in your hand, right? When you take the lace packet, if your ink is going to come, it is going to leach out from the packaging, you're not going to buy it, right? So those aspects, so these are some of the certain phenomena which you have to think, right? And then permeation. So what are the thermodynamic and transport properties while you're thinking of polymers for packaging? So these were all discussed in lecture 58, right? Next, the lecture 59 was on porous polymers and membranes. You know that polymers are used for membranes, right? Do you remember some membrane where polymer is used? There can be ion exchange membranes using polymers. There can be, for example, naphion, right? Fuel cell, naphion, where it permeates, the hydrogen ion movement, right? So these are examples of some membranes where polymers are used. Okay. So what are the different mechanisms by which, material diffuses through polymeric membranes, like solution diffusion? It can be Knudsen diffusion, right? Are you there? Just give me yes or
Yes,
no,
ma'am.
because I may not
Yes,
know
ma'am.
when I'm into the presentation mode. Okay. Right? And then molecular concept of molecular sieves, right? This was all discussed. And then the next discussion was on polymeric foams. What are the different types of polymeric foams? There are, for example, open cell foam can be there, closed cell foams can be there, and how the distribution of pores are there in these polymers. Whether they can be uniform pores distribution, or they can be non-uniform distribution. And how do you create these pores? So these can be through physical means, where the gas molecule is blown along with the polymers, or they can be as a blowing agent, or there can be some chemical reaction which induces formation of some gas molecules, and that creates pores, okay, when they come out and the pores are created, okay. And some examples of polymers where foams are used. Do you remember any polymeric foams? Any polymer foams? Your
No, ma'am.
styrofoam, right? Styrofoam is an example. Okay. So
Yes,
polyurethane, polypropylene foams can be formed. Okay. These are some of the examples of polymers for foams. Okay. Okay. Now, are you able to follow? Can we proceed?
yes, ma'am.
Okay. Sure. Next question. And then polymers at the next lecture was on polymers at interfaces. So obviously, any material will be exposed to environment, so that will have a interface, right? Between the environment. So polymer and air, polymer and water, if it is uh, in some solvent or in some water, okay. Or it can be between two surfaces, a polymer and a metal can be in contact, right? So how the and then what are the polymer interfaces during processing, right? During processing you may have a polymer interacting with the metal surface, right? A mold surface, right? Correct. During processing it may be exposed to a mold surface, a metallic surface, right?
Yes,
And
ma'am.
yeah. So these were all discussed. And what are the interfaces between polymer also? Within the polymeric system also there may be some interfaces. For example, a crystalline and amorphous phase. For example, in a semi-crystalline polymer you will have crystalline phase and amorphous phase, and at a point there will be crystalline phase and amorphous phase there will be an interface formed, right? And that interface in the crystalline and between the crystalline and amorphous region, there will be an interface. So there the property will be different compared to a amorphous domain and a crystalline domain. And also in polymer blends you have two polymers, polymer A and polymer B. And and you have a polymer A domain and polymer B domain, right? And there will be an interface of A and B, that there will be a property, there will be a difference in property at that particular interface also. Okay. And one important concept that was discussed is that, for example, when you have very thin films, what happens in that case is that your interfacial behavior, because the very imagine a very thin film of nanometer size, for example in a polymer coating, for example in paints. Okay, you're painting something, you have some paint, you're coating something with a paint. The thickness of the paint will be of nanometer scale, right? Correct.
Yes, ma'am.
So in that nanometer scale, what happens is that, so there will be a bulk property also, there will be an interface property also, because the paint is also exposed to environment, so there will be some interaction with moisture, there will be interaction with air, there will be interaction with water, correct? So what happens in case of thin films is that this interface in interactions and mechanisms will be dominating the actual bulk behavior, because the thickness is of very 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 small scale, right, of nanometer range. So the behavior is dominated by the interfacial behavior. Okay. uh, okay, you are able to follow.
Yes, ma'am.
Okay. Okay, so anywhere you're not able to follow, just just stop me and just you can ask me. Okay. And then the surface energy of, so when obviously when you have an interface, right, there will be a surface energy associated with it, right? So what is the surface energy, and what is the surface energy of a polymer, and what is the contact angle with the different, for example, a polymer will have a different contact angle when it is exposed to a water, and a different contact angle when it is exposed to oil, correct? So how can you understand the behavior, for example, a polar solvent or a non-polar solvent, or hydrophobic and hydrophilic? So these can be determined by the contact angle, right? And you know uh, and then when you have two polymers, the interfacial energy between both the polymers, so these were all discussed in the lecture, polymers at interfaces. The last lecture of the week was on diffusion in polymers. So here the concept of Fick's law of diffusion and diffusion of water, right? So basically, diffusion in liquids and then diffusion in solids were all discussed. For example, diffusion in liquids, for example, where the Brownian motion, it determines the Stokes-Einstein, it is it determines the diffusion, right? It is where the Stokes-Einstein relation is based on the Brownian motion theory, right? And in case of solids, for example, in crystalline solids, the diffusion mechanism is completely different, right? It is hopping through the diffusion of molecule is through hopping through the crystal lattice, and how this hopping mechanism and all, it is very similar to a random walk in macromolecules that was discussed actually. How they have very similar equations, this diffusion in solid and a random walk in macromolecule. Okay. And how does this diffusion varies with temperature, right? And how does the free volume and diffusion are related, was discussed. And combination of activated energy and free volume in case of polymers, and how does the diffusion in semi-crystalline polymer is determined, and all were discussed in lecture 61. Okay. So these were a brief nutshell of week 8 lectures. Hope you got some idea on what were the things that was discussed in the week 8 lectures, right? You got some idea?
Yes, ma'am.
Okay. Now let's proceed to the question practice assignment session. First question is, match the type of hardness tested with polymers. So, uh, you know, there are three different hardness testers and three different polymers given. One is Shore D hardness tester, next is Rockwell hardness tester, and the third is Shore A hardness tester. Now we have to identify and match which of these hardness tester is used for which of these polymers. Okay, as I told in trade test, it differs from material to material. It differs from differs based on type of material. It differs based on type of application also. Okay, so which of these hardness testers are used for elastomers, which is used for thermoplastics, which is used for thermosets? Any idea?
No, man.
Okay, so okay, so let me proceed with the answer. Actually, show D is used for thermoplastics, and Rockwell is used for thermosets, and Shore is used for elastomers. Okay, and this I have taken a picture from the presentation of the lecture. Okay, and what they do in these hardness testing, whether it is Shore D hardness testing or Shore A hardness testing or Rockwell hardness testing, so this is the polymeric surface. Okay, and they will try to indent the material with a particular load. Okay, and if depending on the dent formed, and how whether it is going to break or it is going to create a kind of a curve in the material, what type of dent it is forming, a particular number is given. Okay, you're able to understand?
Yes, ma'am.
Okay, so depending on that, whether it is going to break, then the hardness, the number, as you can see here, the readings and all, it will be in terms of some number, like it will be some from 0 to 100. So if it is going to, break, then it may have very low, value in terms of hardness testing parameter. Or if it is going to, it is not going to disturb the material, it will have, value maybe 100. Okay, or if it is causing a small dent in the polymer piece, in the polymeric material, it may have something in between, so it is it is having some minor impact. So the depending on this, a particular number is given, and it is used for a particular application. Okay, so these are all basically quick and easy test for commercial point of view. Okay, hope you get an idea, right? Hello.
Yes, ma'am.
Okay, okay, now shall we proceed with the next question?
Yes, ma'am.
Okay. Next question. This is actually a GATE 2013 question. Okay. They've given a viscoelastic fluid is modeled as a spring and two dashboards, all connected in series. Okay. The spring has an elastic modulus G, and fluid in two dashboards have viscosities eta 1 and eta 2. Okay. This question has two parts. In the first part, they are asking for a constitutive equation with that relates stress and strain in this system. Okay, and they also given the dot in the for example, a gamma represents strain, and the dot over strain means it is a time derivative, it is nothing but a strain rate. Okay, similarly for stress also. Okay, now they are asking what is the constitutive relation for this, whether sigma is related as sigma is equal to g gamma plus eta 1 plus eta 2 into gamma dot, or is it sigma is equal to g gamma plus eta 1 minus eta 2 into gamma dot, or is it sigma dot is equal to sigma dot gamma dot strain rate is equal to uh, stress rate by elastic modulus plus 1 by eta 1 plus 1 by eta 2 into sigma, or is it gamma dot is equal to sigma dot by g plus sigma by eta 1 plus eta 2? They are asking what is the constitutive equation. This next part of the question, what they are asking is, for a periodic stress, sigma is equal to sigma naught into e power I omega t. The strain is given by what will be the strain. Okay, so they are applying periodic stress. Periodic stress means it can be sinusoidal, right? Correct. It is having some time period, right? It is oscillatory,
Yes, ma'am.
dynamic, right? It is oscillatory basically. So for that kind of a periodic stress, they are asking what will be the strain. Okay, whether the strain will be equal to sigma naught into 1 by g plus I by omega into 1 by eta 1 plus eta 2 whole multiplied by e power I omega t, or will it be gamma is equal to sigma naught into 1 by g minus I by omega into 1 by eta 1 plus eta 2 into e power I omega t, or will it be gamma is equal to sigma naught plus eta 1 plus eta 2 omega I into e power I omega t by g, or will it be gamma is equal to sigma naught minus eta 1 plus eta 2 omega I into e power I omega t by g. So they have given 4 options. We have to find out what are the options. Okay. Any idea how to proceed with this?
No, ma'am.
Okay. So they have given a fluid, viscoelastic fluid. Okay, and I told you, in phenomenological, modeling, they take the spring and dashboards and all as mechanical analogs, and their combinations they make to, understand the overall behavior of the particular polymeric material or viscoelastic material. Okay, here they have given it is a viscoelastic fluid, and they are giving a spring and two dashboards. Okay. uh, so and they have given that these are connected in series, so this is how the system will look. Okay, so there is a spring with the modulus g and two dashboard connected in series with viscosities eta 1 and eta 2. Okay, so why do you think they have given two dashboards? Any
For
thoughts?
the damping, ma'am.
Huh?
For the damping.
It is actually because one thing you can see from the question, that it is a viscoelastic fluid. So viscoelastic fluid means the dashpot represents viscous nature. So more the dashpots, then more the viscous nature. That is why the material is a viscoelastic. For a viscoelastic fluid, they are having more dashpot elements compared to a spring element. Okay, these are some of the clues with which you can have an idea. Okay, but they can be series or parallel arrangement. Okay, depending on the overall behavior. But these give some idea that they may be more of a fluid behavior. That is why they are having more of viscous elements, viscous mechanical analogs compared to a elastic mechanical analog. Okay, now in the question they have given one spring and two dashpot in series. So for a series combination, the case is that the stress is same across each element. What does that mean? The stress is same across each element.
Stress remains constant.
Yes, the stress is constant. That means the stress in this spring element is equal to the stress in this dashpot element, and which is equal to the stress in the second dashpot element also. So sigma 1 is equal to sigma 2 is equal to sigma 3. Whereas the strain is not the same. The strain by the spring element will be different from the strain by this dashpot element and the strain in this dashpot element. So the total strain will be a summation of the all the three strains. Okay, so the total strain will be gamma is equal to gamma of spring plus gamma of dashpot 1 plus gamma of dashpot 2. Okay, now how to proceed further? The next step is that we have to develop the relation between the stress and the strain, right, for developing a constitutive relation. So for spring, Hookean spring, we know that stress is proportional to strain and the constant of proportionality is modulus, right? So we are just, so sigma is equal to g into gamma. So gamma is equal to sigma by g. That is what we have written here. Okay. Next, for dashpot element, okay, it is strain rate is proportional, stress is proportional to strain rate and the constant of proportionality is viscosity. So rearranging that, strain rate is equal to stress by viscosity. That is what we have written in the second part. Okay, so for dashpot element 1, it will be sigma by eta 1. For dashpot element 2, it will be sigma by eta 2. Now we have three relations, correct? Now we have to combine these terms to form overall constitutive relation. So how do you combine? Any idea? Any thoughts?
No, ma'am.
Okay, no worries. Let's proceed. So these two are in terms of strain rate. This is in terms of strain, correct? So what we can do is that, so we also know that overall relation strain is equal to, total strain is equal to summation of individual strains. So gamma is equal to gamma s plus gamma d1 plus gamma d2. So we can also just modify this. We can just differentiate on both sides. So d gamma by dt is equal to d gamma s by dt plus d gamma d1 by dt plus d gamma d2 by dt. We know what is the relation for this d gamma 1 by dt and d gamma 2 by dt from the dashpot elements, right? Because they are already in terms of strain rate. But what about this spring element? We just have to differentiate this expression. So that will give you d gamma s by dt is nothing but your d sigma by dt multiplied by 1 by g. So that you can just write that is, so d sigma by dt is nothing but sigma dot. So your total strain rate is equal to sigma dot by g plus sigma by eta 1 plus sigma by eta 2. So just rearranging it, you get sigma dot by g plus sigma into 1 by eta 1 plus 1 by eta 2. So this is what is the constitutive relation for this system, which is actually the option 3 given in the question. Okay, you're able to understand?
Yes, ma'am.
Okay, now let's proceed to the part B of the question. Part B, again, they have given you are applying some periodic stress, right? And they have asked what is the strain. So for the spring element, you have the direct relation gamma s is equal to sigma by g, which is equal to sigma naught into e power I omega t by g, right? Now for the dashpot element, we have strain rate. So gamma dot is equal to sigma by eta, which is nothing but equal to sigma naught e power I omega t by eta. Now this is in terms of strain rate. Now how do you find expression for strain for the dashpot element? It is just simple mathematics what you have to do. What do you do to convert strain rate to strain? What operation you have to perform? What mathematical operation you have to perform? It is nothing but you have to integrate, right? So integration of d gamma by dt will give you gamma, correct?
Yes, ma'am.
Yeah, so you have to perform integration. So integrating above equation, you will get gamma is equal to sigma naught by eta. Those two are constants, so you do not disturb that. Whereas e power I omega t, when you integrate it, you will get e power I omega t divided by I omega, correct? So
Yes, ma'am.
now this I omega, this is a imaginary term, right? When you have imaginary term in the denominator, you just multiply with that once more. So you multiply with I omega in numerator and denominator, and you will get sigma naught into I omega e power I omega t by eta into I square omega square, correct? I square is nothing but minus 1, correct? I is nothing but square root of minus 1. So I square is square root of minus 1 into square root of minus 1, that is nothing but minus 1. That is what I have written here. It is minus I. and omega by omega square you will get cancelled, so you will have omega in the denominator. So the overall expression for strain for the dashpot element will be minus I into sigma naught by eta omega the whole multiplied by e power I omega t. Now we have two dashpot elements, right? So for both the dashpot element you will have similar expressions. Only thing is that your viscosities will differ. So substituting the values, you will get gamma is equal to sigma naught into e power I omega t by g for a spring element, and for dashpot element 1 it will be minus I into sigma naught by eta 1 omega into e power I omega t, and for dashpot element 2 it will be minus I into sigma naught by eta 2 into omega in omega multiplied by e power I omega t. So rearranging it, you will get the total strain for this periodic stress given is sigma naught into 1 by g minus I by omega into 1 by eta 1 plus 1 by eta 2 e power I omega t, which is nothing but your option 2 given in the question. Okay, you were able to follow it. Just integration operation you have to perform. The earlier to get the phenomenological model you did differentiation, here you're doing the integration, just mathematical operation you're just doing, and then substituting the respective terminologies, right?
Yes, ma'am.
Okay, so this is in fact a gate question. Next question. Identify the correct statement according to Griffith's hypothesis for a crack to increase in size. So, for a crack to increase in size, according to Griffith's hypothesis, should the rate of stored elastic energy decrease be greater than or equal to the rate at which surface energy is created during crack growth, or should it be rate at which the surface energy is created during crack growth is greater than the stored elastic energy decrease, or is it the stored elastic energy decrease is equal to the rate at which surface energy is created during crack growth, or is it the rate of stored elastic energy increase is greater than the rate at which surface energy is created during the crack growth? Which of these is correct according to Griffith's hypothesis? Any idea?
I guess it's D, ma'am.
You're saying B. So the rate at which the surface energy is created during crack growth should be greater than or equal to the rate of stored elastic energy decrease, you say. Okay. It is
Yes, ma'am.
actually option A. This is according to Griffith's hypothesis. So the decrease in elastic energy. So in a polymeric material, there will be some elastic energy stored. So when the crack starts to propagate, this elastic energy stored gets lost. So this loss in elastic energy should be higher than the new surface energy created. Then only the crack can grow and the new surface can be created. Okay. So that this is what, and the crack starts growing. Okay. So this is what is the Griffith's hypothesis. You are able to understand?
Yes, ma'am.
Okay. Next question. Surface resistivity is related to volume resistivity, a material property as. So when we were discussing the recap of lectures, I told that surface resistivity is kind of a trade test or particular application related property, whereas your volume resistivity is your actual material property. Okay, this trade test property and your material property are correlated. How is it correlated? Any idea?
No, ma'am.
Okay, it is actually your surface resistivity is equal to your volume resistivity by T, Tt. Okay, where T is the thickness or the thin layer through which the conduction occurs. Okay, thin layer of the surface through which conduction occurs. Uh, this is how it is related. Okay. So surface resistance is nothing but resistance offered when 2 points on the surface are probed. It is It is measured you by probing the surface at 2 points. Okay, and what happens is that in practical surfaces, the surface may not be a pure polymer. So for example, a surface is getting so surface is always open, right? So the surface may have impurities or dust or moisture, and because of accumulation of dust or moisture or some impurities, the conductivity in the surface will be different, and so that will have a thin layer. Okay, due to these deposition of these materials and all, so that thin layer, so if you divide the volume resistivity by that thin layer of surface, you will get what is the surface resistivity, which is a measure for particular application. Okay, and this measure, it will differ depending on application. For example, in some application the surface may be exposed to dust. In some other application the surface may be exposed to moisture. Okay, so depending on the application, the surface resistivity value will differ, whereas the volume resistivity will not differ. The volume resistivity is a constant, okay, for that particular material. Okay, you are able to follow?
Yes, ma'am.
Okay. Critical stress at failure is related to crack length. How is it related? Is it directly proportional to crack length, or is it inversely proportional to crack length, or is it directly proportional to square of crack length, or is it inversely proportional to the square root of crack length? How is it related? How is critical stress related to crack length? Critical stress of failure, that is the stress beyond which you can see failure. How is it related to crack length?
Inversely proportional.
Okay, you're saying it. So there are two inverse relation. So which one you're saying? You're saying option B or option D?
D, ma'am.
Huh?
D.
B. You're saying
A, B,
inversely
B.
proportional to crack length. Okay. Okay. Let's see what is the actual answer. It is actually inversely proportional to square root of crack length. Okay. So this is how is the relation. Okay. So you have sigma c is equal to 2e gamma surface by pi c the whole power half. So c, where c is the crack length, so it is related inversely to the square root of crack length. Okay, you're able to follow.
Yes, ma'am.
Okay, and this also gives the answer for the previous question, the Griffith's hypothesis. So for a crack to increase in size, the rate of stored elastic energy decrease should be greater than or equal to rate at which surface energy is created during crack growth. Okay. Now let's proceed with the next question. Phenomenon of polymer undergoing plastic or viscoelastic deformation till failure during cyclic loading, which is usually less than the strength of the polymer, is what is this phenomenon called? Where the polymer undergoes some plastic or viscoelastic deformation till failure, that is, the material ultimately fails. But this failure happens due to a cyclic loading, and the load is actually less than the strength of the polymer. So what kind of phenomenon happens? What is the phenomenon called as? Any idea?
No, ma'am.
Okay. Okay, it is actually fatigue. Fatigue is where the plastic or viscoelastic deformation occurs till failure. The material ultimately fails due to cyclic loading. Okay. So this cyclic load which is applied, it will be less than actually the strength of the polymer. Okay. Uh, Next question. The number of cycles to failure dash with increase in stress amplitude. So, does it increase with increase in stress amplitude, or does it decrease with increase in stress amplitude? Or
Decrease of.
uh, it decreases, you're saying.
Yes, ma'am.
You're right. So the number of cycles to failure, it decreases with increase in stress amplitude. As stress amplitude is higher and higher, the number of cycles it takes to fail will be lower and lower. So this is what is the relation, fatigue or endurance limit relation, okay, with stress amplitude. So higher the stress amplitude, the lower is the number of cycles to failure. The lower the stress amplitude, it can undergo more number of cycles before it it fails, ultimately fails. Okay. Next question. Lower fatigue resistance for thermoplastic is due to, what is the reason behind low fatigue resistance for a thermoplastic material? Is it because the elastic part of deformation during cyclic loading leads to increase in temperature, or is it viscous part of deformation during cyclic loading leads to increase in temperature, or is it elastic deformation during cyclic loading leads to increase in temperature, or is it plastic deformation during cyclic loading which leads to increase in temperature? Which of these causes?
Second option.
Viscous part of deformation, you say. Okay, this is for thermoplastics. You want to take another guess?
C, ma'am.
You're saying C.
C.
C. That is elastic deformation during cyclic loading.
Yes, ma'am.
Okay, it is actually option D. Okay, the plastic deformation, okay, during cyclic loading leads to increase in temperature. Okay, and that is what is the reason behind low fatigue resistance for thermoplastics. Okay, next question. Migration of molecules from polymer phase to environment or to some other surface which is to which it is exposed to, it is called, what is it called? So material migrates from polymer phase to some, say for example, if a polymer is there in water, some material, uh, you know it moves from the polymer to water phase. What is this phenomenon called? Any idea?
Permeability, ma'am.
Hmm?
Permeability.
Permeability is a property. What is a phenomenon called? No, it's not a property. It's again, it's uh, what is it called? It is actually leaching. Okay, when material transfers from a solid phase to a fluid phase, it is called as leaching. Okay, permeability is again a property, material property, and the phenomenon here it is called as a leaching. Okay, the next question is, oxygen transmission rate is a dash test while permeability is dash. I just now told the answer for the second part.
Second part is property, ma'am.
What property? What is then oxygen transmission rate?
No, no, ma'am.
Hmm?
I don't know, ma'am.
Okay. Oxygen transmission rate is actually a trade test. Okay. Whereas permeability, with permeability also you can identify how much oxygen permeates through the for example a particular polymer. But this permeability is a material property, whereas oxygen transmission rate is a trade test. Okay, and in fact in the lectures, lecture it was discussed, where for example in case of polyethylene the oxygen transmission rate is higher, and Similarly, permeability for oxygen is higher. So how what material property and trade test gives, uh, they give similar results, and how really trade test can be used as a to give a idea, especially for commercial applications and all, industries, they can do the trade test and get an idea whether whether the oxygen transmission rate or the way the amount of oxygen that will get transferred into the through the polymer, through trade test they can really give have an estimate. Without doing actually understanding the permeability of the material, they can do these trade test and find out. Okay. The next question is, in nuts and diffusion, the pore size is very large compared to the molecular mean free path, or the pore size is very small compared to the molecular mean free path, or the pore size is of the order of the molecular mean free path, or the correlation of pore size and molecular mean free path is irrelevant. Which of these option happens in nuts and diffusion?
Fourth option, ma'am.
There is no correlation. Same. Is it? Okay, let's see what is the answer. It is actually in nuts and diffusion, no? The pore size is of the order of the molecular mean free path. Okay? Okay. Now let's proceed to the next question. In solution diffusion mechanism, in order to have a higher permeability, should the diffusion coefficient be higher and solubility be lower, or should the diffusion coefficient be lower and solubility should also be lower, or should the diffusion coefficient be lower while solubility should be higher, or both diffusion coefficient and solubility should be higher? Which of these should be uh, you know there in order to have a higher permeability in case of solution diffusion mechanism?
Both diffusion and solubility, ma'am.
You're saying for solution diffusion mechanism, the diffusion coefficient should be lower. Okay, diffusion coefficient should be lower. And what about the solubility?
Fourth option, ma'am. Both diffusion coefficient and solubility should be higher.
Yes, you are right. It has to diffuse, and the diffusion coefficient should also be higher, and the solubility of the material should also be higher. Okay, this is what is the relation. So permeability is kind of product of your diffusion coefficient and solubility. Okay, now let's go on to the next question. Interstitial C is defined as, what is the definition of interstitial C? Is it lattice atom displaces diffusing atom to an interstitial position, or diffusing atom displaces lattice atom from interstitial position to lattice position and then it occupies a interstitial position, or is it diffusing atom displaces lattice atom from lattice position to interstitial position and it occupies a lattice position? This basically happens in solid diffusion uh, with crystalline crystal lattice. Which is the definition of interstitial C?
Second one, ma'am.
You're saying that diffusing atom displaces lattice atom from interstitial to lattice position and it occupies the interstitial position, you say. Okay, it's actually the diffusing atom, it displaces lattice atom from the lattice position to an interstitial position and it goes and occupies the lattice position. Okay, hope you got it. Let's proceed to question number 11. Diffusion in amorphous domain is impeded by obstacles in crystalline domain. Is it true or false? Is it true or
True,
is
ma'am.
it true? Okay. Why do you think it is true? Why do you think it is true? Any thoughts? You're right, it is true. Okay, when there are crystalline domains, uh, as you know, in the crystalline domains, the diffusion, uh, is difficult because of the ordered arrangement. The molecules, it finds it difficult to diffuse. We know that the diffusion coefficient, for example, for a liquid is higher than that of solids, and the gas is higher than that of liquid. So one of the main reason for that is that in crystalline domains, or in crystalline solids, in the crystal lattice, it is not so easy to actually the material to diffuse. Okay, it is not so easy to displace the atom as we saw in interstitial C and all. No, it is not so easy to displace the atom from a lattice position and all. So that actually creates an obstacle. For example, in polymers, you have semicrystalline polymers, you have amorphous and crystalline domains. So it is easy to pass through the amorphous domains. So when there are crystalline domains, the diffusing molecules, it takes up around about through the amorphous domains and leaving the crystalline domain. So it has to go through the obstacle of the crystalline domain, okay, in order to diffuse. Okay, the last question for the session is, data at higher temperature can be correlated to dash time in master curve. We know that there's time temperature superposition and all possible, right? So how do we relate the higher temperature to time? Is it higher times, or is it to lower times? Higher temperature can be correlated to, for example, years and days, or is it correlated to seconds, picoseconds? The behavior at high temperature.
Don't know, ma'am.
Okay, it is actually higher temperature is correlated to a longer time. Okay, higher temperature means, for example, at higher temperature there will be more of a segmental flexibility. Correct. So this can also be correlated to a you're estimating the material behavior at a long time. Giving ample time for the material to relax and all. Okay, whereas your behavior estimated at lower temperature can be related to very low times. That means picoseconds. So at picoseconds the material is not really able to respond, and it will show more of a kind of the segments cannot move in that picoseconds levels. So what happens is that the materials would show more of a glassy kind of a behavior. Okay, so this is what this is how the master curve. So low times, kind of a solid like elastic like behavior. Okay, this is at low lower temperature. For example, here it is showing some negative temperature of minus 270 or something, whereas at high temperature like 290 or something, the material so the material shows kind of a more of a viscous or Newtonian kind of a behavior. Okay, and this can also be correlated to you're giving ample time for the material to relax, and it is showing more of a fluid like nature. Okay, that is what, and that is how you develop the master curve. Okay, I hope you are able to get it.
Yes, ma'am.
Okay, so that is it with the session. So any doubts you have?
No doubt, ma'am.
Okay, if no more doubts, then we can officially close the sessions. In case you have any further doubts, not only in the session content, even in the lectures or anything, you can put forth your question in the forum, and also you can ask in the next live session as well. Okay.
Okay, ma'am.
Okay, fine. Yeah, thank you. Have a nice weekend. Anything else you want
Thank
to
you.
say?
No, ma'am.
Okay, fine. Thank you.
Thank you, ma'am.
Thank you.